Why is everybody sitting so far? Okay, don't that you can answer it, but anyway, it's fine if you sit far. That's okay. But try to focus. You're here, so make use of the opportunity to think about a new topic which you'll not see in other courses in the program. So we are here. So we have one more lecture to go for the actual lecture content, and then we are going to kind of start focusing on projects, because that's a big component of this course in terms of grade. So we will have a meeting, and again I'm going to send out slots for meeting times, and it's basically about tuning up your report. Okay, so generally what happens is you are kind of scrambling for enough results. Sometimes you have results, but there may not be enough for the project. So it's a good I know it's right before, a week before the submission, but it's kind of useful to get a fine-tune your projects. Okay, and so that's the purpose of that. And then we'll have presentations. Both of them will take place online, because it's trying to keep things efficient. So with that, let me come back to we've seen a lot of things over the course, and it's important to not lose an idea of the bigger picture, as in the overall context. So we have been for the first several lectures, we've looked at a variety of models, feed-forward, CNNs, and then embeddings, word embeddings, and then sequence models, and then transformer architectures, basically. And then we also saw some additional architectures, but they were not exactly related to supervised learning, but still we're using unstructured data, in particular images here, variation autoencoders and GANs. Okay, so we've been covering a lot of models, neural network models, and since the past 2 lectures, we shifted gears to focus a little bit more on decisions. Okay, because it's something that a typical data scientist or a business analyst may not see if you are too far away from the business goals. But generally, sometimes you are part of a team which is part of a product development organization, and then there has to be some actuation of your forecasting or your predictions. Okay, so generally, whatever you've seen so far, let's say we include unsupervised deep learning as well, it's more about perception. Okay, so I guess in the computer vision world they call it perception, but it's mostly forecasting. And then there is a component which is, once you generate forecast, what are you going to do, right? And so for that, we kind of shifted gears, and we were talking about decision making in general. So one simple thing that you can do is, whatever forecast you generate, there are a bunch of numbers or classes or whatever they are, right, which a pre-trained model or trained model can give you on a test data. And then those data points, those predictions become input to some sort of a decision making tool. Okay, so for example, I don't know, some of you are doing revenue management or supply chain management and things like that. So there will be some optimization problem that they are trying to solve. Okay, and so whatever you forecasted, expected future demand or expected return on investment, things like that, they will become numbers in an optimization problem. Typically, if you think of an optimization problem, you don't have to do an optimization problem. You can always do Excel-based planning and things like that. But at the end of the day, they become numbers, and then you can always make decisions. Okay, so you can solve the optimization problem and so on. But the version of decision making that we are studying is a particular narrow topic in this broader field of decision making, which focuses more on the problems that involve some sort of learning while making decisions. Okay, so you may say, hey, how can I? So in the process that I mentioned, where you build a prediction model, batch data, then you use that model to get some numbers. Those numbers become inputs to your decision making setup, whatever it is, optimization problem, for example. That's one way. But here, this series of lectures are focusing on doing that or a version of it in a for loop. Basically, you can kind of compress this whole training from batch data and making predictions to some sort of a an abstract learning step. Okay, so we'll see simple learning things. We saw simple learning things, and I'm going to connect it back to that. But we have some learning step. we make some decisions, and then we observe feedback, and then you kind of repeat it again and again and again. Okay, so that's a specific version of decision making. It's not exactly the previous version I mentioned, where you build a model, get some numbers, and then plug that into an optimization problem. That's also a decision making setup, but that's not what we're focused on. Here we really need that for loop. And so we started with, okay, let's drop all the complicated learning techniques that we know, in the sense that, drop deep learning, let's drop even shallow learning. Let's just focus on, if there was a mean reward for each arm in a multi-arm band setting, which we don't know a priori, how can we learn while trying to make decisions such that we can, kind of adaptively make the decisions which are actually good. Okay, so you don't know a priori which what the unknown number is, mean reward, for example, each arm, and then we are trying to make decisions which are picking an arm or picking a decision such that based on adaptively, which just means that based on previous data. So there is learning involved, but it's only focused on trying to make the better decision more often. Okay, so that's the simplest setting, where you have this for loop. The learning process is very simple because there's just one unknown number. You're just trying to estimate it for each of the decisions that you're making. We started with that, and we talked about contextual learning and its relationship to supervised learning a little bit. Okay, it's very similar to supervised learning, except the big key ingredient is what's called bandit feedback, right? So you make a decision, you only know how that decision fared in terms of reward that you get, maybe sales or something like that. You don't know what would have happened if you took a different decision. Okay, what if you stocked more units, or what if you stocked less units? What would have happened, right? So that's a big difference between contextual bandits and supervised learning. Okay, and that's why there's some gap in terms of how you would use. You can always use a supervised learning technique for a contextual bandit setting, except that you will know there will be parts where it will be wrong. Okay, because you don't know what would have happened if you tried something else. And so that was the starting trajectory, and so we continued down that line. So the broader level, and we'll get into weeds in a second, so I just want to keep the broader context clean, which is that we're still going to look at this loop of you getting some information from the system or a state or the world. We'll just call it a state. You will take some action, and then action will yield a reward, immediate reward, and then you kind of again get to a new state of the world. You take an action, you get reward, and so on. So that for loop is still there, except now you care about taking actions which may have long-term consequences. Okay, so that's why. So you cannot make it into a supervised learning problem anymore, because there is temporal dependency. So you taking action today has impact on the next observation 1 week later, and so on. So it's not really, it's not batch data anymore. I mean, it's you can batch it, but it's not IID data and so on. So there's some gap there. So we'll get started. We kind of looked at that last time. We introduced up to what is called a Markov reward process. We'll get back to that and review that in a second. But today's objective is to kind of finish up that treatment and get to one algorithm. Okay, and the algorithm is going to be pretty intuitive if we understand Markov reward process and that recursion that I was talking about. We'll visit that in a second. Recursion just means the relation between state value function at one state and state value function at some other states. Okay, so we'll look at that, but that kind of will lead us to an algorithm called Q learning. Okay, and so that's an example algorithm we'll look at. So that's the objective for today, and hopefully we'll also we'll try to cover a little bit on function approximation from lecture 12, and then leave the remaining 2 topics for next hopefully next lecture. Okay. So that's the plan. So really kind of get exposed to Q learning. That's the key core thing that we want to get to today, and then talk about something called function approximation. And so next lecture actually ties back the strings together. It keeps this for loop of look at the state, make some decision, get some reward. That loop is still there, but now look at the state, make some decision. That mapping is a neural network. Okay, that's what's going to happen next time. So we'll come back to neural networks next time, but for today we'll kind of focus on this algorithm. Yeah.
Both the methods will be the same model.
The model architecture could be the same. So you could use the same CNN or the same feed-forward neural network. It's just that they may take different predictions. They may make different predictions if you really focus only on the neural network part. So if you just think of supervised learning, they'll make some short myopic predictions, whereas the networks trained here will make non-myopic predictions. So they may say a different label only because that label or that action may lead to a better reward later on, for example. we'll talk about again talk about the relationship, maybe when we go through the material. So I kind of explain the goals without looking at the goals page, but let's look at it. Yeah. So last time, the objective was to kind of get started into reinforcement learning as an extension to contextual bandits, and then we saw basics of not Markov decision process, but just Markov reward processes, and we'll talk about MDPs today. And last time we did talk about what is the policy, what is the value function, and we saw one recursive equation for value function for a Markov reward process. So we'll come back to that. Actually, these two will be related, okay, and we'll kind of see that today as well. So as I said, RL agents, like if you think of RL, so for example, Zoeb will have his own policy, for example, and let's say Shubham has his own policy. It's like you guys having your own policy, interacting with the environment and getting some rewards. Whether Zoeb uses a technique based on just learning policies directly, or whether Shubham uses a technique which relies on value function behind the scenes, but at the end of the day, you still have to take an action. Okay, so therefore, policies and value functions will be related, and so we'll talk about that relationship today. Okay, but the algorithms each algorithm can have its own internal way of computing things of what's the best thing to do in each state or each situation. That internal behind the scenes stuff could involve value function, need not involve value function, or it could involve both, or could involve what is called a model. So there are many things that an agent or a software or any person can do behind the scenes, but at the end of the day, they have to still take an action at every state. But they are related to each other. Okay, so policies, value functions, and models. Today's goal is to understand. So I guess the first, preliminary goal will be to understand the difference between what's called an expectation equation and an optimality equation. It's not super important, but in the grand scheme of things, but it is important for understanding, motivating us towards the Q learning algorithm. Okay, so everything, as I said, is centered about getting one approach, one algorithm for this reinforcement learning setup. Okay. Remember, in contrast, for contextual bandits, we had one approach called EXP4. For multi-arm bandits, we had like several approaches: epsilon greedy and UCB and Thompson sampling and EXP3 and several approaches. But here we're only focusing on one. Okay, just because the whole infrastructure, this whole notion of Markov chain, Markov reward process, Markov decision process, they're all new for us. So we just want to pick up the right things and just focus on one core algorithm and learn it, right? So we'll try to just intuitively reason about this algorithm. So there's some update rules. It's going to be an iterative algorithm, very similar to UCB and other ones. So we'll look at what the updates, what does it update, and does it make sense or not? And of course, one of the goals is also to, as I said, even in the previous one, is a relationship between a new object that I'm going to introduce today called state action value function. So state value functions that we saw last time are something like V of S. Okay, so for every state, there's a function which maps it to a number. Higher the number, the better the state is in terms of from the agent's perspective. I want to be in those states. So similarly, state action value function is a very, very related function to the state value function, and I'm going to introduce that, and they're related to each other. In fact, this symbol Q kind of represents that, is a kind of a canonical, notation for talking about state action value function. So we're going to kind of relate that to things that we saw last lecture. Okay? In particular, state value function and policies. Okay. So any questions about the goal and the overall context? Okay. If not, I just want to check if we are recording, and I don't know if anybody can hear me, but I hope they can hear me. Just open chat as well. Okay, so I'm gonna start at a slightly different point, which is in slide 27. What we're gonna do is introduce again, quickly recap Markov chains, Markov reward processes, so that we can spend a little bit more time on Markov decision process. Okay, so this is something that we covered last time. So we have covered slide 27, for example. We have gone up to some slide 40 or something, but I'm just gonna recap that. Okay. it's new material. You may say, hey, what's the benefit of me learning this? It's basically a different perspective, right? You're not just function fitting, which is, I guess, mostly what you do. At least as a starting, there's a bunch of problems which just fit into supervised learning bucket, but there are a bunch of problems which don't. And so this is I guess, a perspective you want to kind of build for one set of problems, which are reinforcement learning problems. Okay, so with that, let me recap. So for this section, the objective is to really kind of get a feel for Markov decision process. What is it? What is it? How is it defined? Okay, it's an object. Think of it as an object, like a Python object, right? So it has to be defined in terms of some variables, right? And we'll talk about states, actions, transition probabilities, reward function, and then some discount factor. Basically, that's what it is. So we want to get to a definition of MDP because it's going to be useful for us, not the object itself, but the components, these components, state, actions, things like that. But while getting there, there's one important thing that we want to focus on, which is the notion of value function and the recursion related to that. Okay, so those are two things we want to kind of get for today, for this part of the, I guess, this part before we get into Q learning, I guess. Okay, so we are in this second bullet point here. Okay, so last time we saw what is a policy. Policy is a function which maps from state to actions. Here I've generally shown it as a stochastic policy, which means that it's a distribution over actions given a state. So it's a conditional probability. Okay, so condition on a state. Maybe there are 3 actions. Then action 1 is with probability 0.4. Action 2 is with probability 0.6. Action 3 is probability 0.0. 0. Then that's a distribution of actions, and so that's a policy. So the output space, if it's a deterministic policy, will directly tell you what the action should be. Whereas if it's a stochastic policy, it will tell you with this probability, this is the action, with some other probability, this is another action. So the output space is going to be a vector of probabilities, okay, from which you can further sample and take an action. Value function is notated by a subscript pi, typically, unless if we are not doing that, it's typically assumed, or there has to be some difference. So we'll point that out if we don't add an extra pi there. So it's just saying if somebody picks a policy, like Zoe picks a policy, then under that policy, each state has a value. Okay, some states are kind of not good to be in, and some states are good to be in according to that policy because we are following that policy. And so that's what the value function is intuitively. Okay. Last time we introduced some random variable called the return random variable. I'm going to recap that in a second. So value function at a given state is the expectation of that return random variable. Okay. We'll go through an example again just to see what it is. And then the model components are not exactly necessary for the RL problem, because in RL, remember, the problem is you don't know anything about the environment, just collect as much reward as possible. So it's very similar to the MAB setting, multi-arm binary setting, where you don't know anything about the return or the average returns of each of the arms, but just learn and try to take the best action, right? So RL problem is exactly that. Remember, if we motivated it last time, is you're in an environment or you're playing with a simulator. For example, typically think of a game, right? You don't know what actions will lead to high scores, but as you play, do trial and error, figure out what's the best set of actions to take so that you can maximize your score. Okay, so that's the RL problem. So we don't actually need to know a priori the model. Okay, that's because we're interacting, right? So remember, our for loop was we got exposed to a state, we do something, we get some reward. Right? We keep repeating that. Okay, so the API for us is I need to get the state information. I send some action information, and I keep repeating. I learn because sometimes I'll try some actions which are bad, and I learn that, hey, these are bad actions, and then maybe next time when I'm in a similar state, I'll not do that action, things like that, right? That's learning, right? So if you remember last lecture, we don't need this a priori, but what an agent can do is learn these transition probability kernel and the reward function by interacting with the environment. Okay? So it can learn. So an agent can learn any of these things. Okay, agent can learn focus on only this. Agent can learn just this, or agent can learn just this, or all 3 of them. Okay, that's the RL problem. In the MDP framework, we're going to step back a little bit, into a more basic situation where we'll say, how do we even talk about these states and how they, and about policies and value functions and how they relate to each other. We are dropping the learning aspect for now. Let's say these are given. How are they related to each other? I guess that's the focus when I'm motivating the MDP. We'll again come back to learning in a second, because we haven't seen any algorithm yet for solving the RL problem. The only algorithm we'll see is the Q-learning algorithm. Okay, so don't think in terms of algorithms or what, don't think of algorithms at the moment, I would say. Yeah. So with that, disclaimer. So it's just as I said, MDP is just a way to describe an RL problem. It can also describe just a MDP. So MDP itself is a description of a problem, okay, a sequential decision-making problem. And the way we're going to motivate it, and we started last time, is start with a Markov chain, then talk about a Markov reward process, and then talk about an MDP. And there's going to be a gradual increase in extra components when we're describing this. Okay. So Markov chain is Markov chain is just a collection of random variables. Okay. Indexed by an ordering index like time. And so if you have a collection of random variables, and these random variables are not independent of each other. If they were independent, there's no Markovian here, and it's basically independent random variables. So Markov chain has a Markovian property that the random variables satisfy, in the sense that the random variable which is at the 10th index has nothing to do with the random variable in the first index, given the 9th index random variable value. Okay, so that's a Markovian property. So history doesn't matter for the next random variable given the current random variable's value. Okay, so that's a Markovian property, and that's all. Markov chain is just that. It's just a collection of random variables. And so you think about, hey, what are the values that these random variables are taking given this Markovian structure? Okay. And then last time we also saw Markov reward process, which just adds rewards as some numbers that get emitted every time you take a state value. Okay, so let me explain that via two examples that we saw instead of looking at equations. I just want to mention that for Markov chain, your primary object that if you want to learn, then the primary object you want to learn is this. But for us, if you want to describe a Markov chain, all you have to describe is this transition probability matrix. Okay, and it's a matrix only because I'm assuming that the number of states is little n. And I'm assuming that from every state, at least not assuming, but I have little n number of states. That's what I'm assuming. And let's say I'm also this is not the only thing. Sometimes you also need to know the starting state. What is the probability of starting in some state? Sometimes in some Markov chains the starting state is fixed. Hey, you always have to start from state value 1. Okay, then you don't need an extra information there. I mean, that is the information. Sometimes what happens is your starting state itself is drawn from a distribution. So you draw what is the starting state value, and from then onwards you can just use this matrix to realize the random variables. Okay, this matrix is basically describing the joint distribution of these random variables, this chain of collection of random variables. Okay, and so each row is basically a probability mass function. It's just saying, given state 1, what's the probability of me going into state next random variable taking the value 1, and next random variable taking the value little n. So these are the probabilities. The row sum has to sum to 1 because of the probability mass function. Okay, and we saw that with this example here. Here the circles represent the states. States are the values that the random variables can take. Okay, and so a random variable, let's say the first random variable can take a value class 2, then the next random variable can only take value sleep or class, because there are only 2 outgoing edges here. Okay, so that's the dependency. So given the first random variable, the second random variable is kind of restricted. It cannot take a value pub or something else. At the same time, given class, the next random variable is kind of independent with respect to some previous values, like maybe independent of the previous random variable, which might have been pub or might have been class or something else. Okay. So this is an example where we said, okay, let's say we state the chain, the starting random variable, the first random variable, S1, capital S1, takes a value C1, let's say stands for class 1. Then given that, the chain evolves kind of autonomously, in the sense that you're just a passive observer. There's a collection of random variables. If I tell you the starting state, you can draw a realization, okay, without intervening. Okay, remember, we eventually want to connect it back to Markov decision processes, where there's going to be actions where we say, hey, take an action this in the state. That's not there here. It's basically, hey, this is the starting state value C1. From here onwards, what can realize? Okay, what can realize is, okay, maybe from C1 you can maybe go to C2. You could also have gone to Facebook, but in the first row, it just happened that from C1 you went to class 2 instead of Facebook. Okay, that's just an outcome, right? Random outcome. Similarly, from C2 you went to C3 and so on. So these are just realizations of the collection of random variables. they are of different lengths only because when you hit this, when you get to the sleep value in this state space, there is no outgoing edge, which basically means that you kind of continue to take sleep values forever, and so so that's what it kind of informally means here. Okay, so there is length of you can see that this one has a length of 5, here's a length of 6, and some are much longer. Okay, so this is just jumping around next random variables, taking certain values given the previous random variables. Okay, any questions about this? Okay, so here's the example for this diagram. Instead of showing a diagram, you could have just directly shown the transition probability matrix, because we also specified that the starting state is always C1. So from C1 we can only go to C2 or Facebook. If you go to let's say we went to Facebook, from Facebook you only can go back to C1 or Facebook and things like that. So we can just see what the transitions can be and what transitions are not allowed. And row sums are always 1. So 0.5 plus 0.5 or 0.1 plus 0.9, they should sum to 1. Okay, so with that, what we're going to add is one extra component, again completely autonomous, in the sense that once you specify the starting state and the transition probability kernel, states gets realized in their own way. But when each state value gets realized, we're also going to generate a number. And to generate the number, we need to have an extra function, and that function, so we're going to have an extra random variable rt plus 1 if it's in a state st. Random variable st takes a value little less, then given that value, there's going to be a random variable rt plus 1 that gets realized. Okay, that's a number, that's also a random variable which takes a value, let's say between here there's no need for any restrictions, so let's say it takes a real number, okay, some value, then that is an extra thing that you add. Okay, so that's denoted by this function scriptar here. Scriptar is a function, so don't worry about the subscript here. It's just you can also write r bracket s or something like that. And also there's one extra component that's needed, which is gamma, because what we'll see is that we're going to start summing up these reward numbers. And so if and in particular we are describing a Markov chain which doesn't necessarily terminate. Okay, so actually in the previous example, the Facebook one, once you hit sleep, you're not going anywhere else. Okay, so it kind of eventually terminates. You cannot always be jumping around. So gamma is just an extra number to ensure that when we add up reward numbers, then they don't blow up. Okay, so that's the motivation. It's something like time value of reward or time value of money concept, if you have seen it in finance classes. Okay, so because we added this extra number, so remember the chain is generating state observations autonomously, and every state it's also generating reward numbers autonomously because there's a function already defined. And so at any given point of time t, I'm gonna get a bunch of numbers, right, based on the next state that gets realized, given the state, some reward that gets realized, and so on. So what I can define is a new random variable, which is a derived random variable, derived just because that random variable is just a sum of all these r random variables, reward random variables, okay, from that time onwards. Okay, so gt is equal to just rt plus 1 plus gamma rt plus 2 and so on. So this discounting factor gamma is exactly doing that work, where if there was no gamma, this would be a sum, and the sum could blow up to infinity. So this gamma ensures that the sum will not blow up to infinity as long as each of the reward random variables is bounded, in the sense that, for example, each of the rewards, let's say it's only up to $1, right? So if you don't give gamma, then $1 plus $1 plus $1 plus $1, it can go up to infinity. But if you give a discount factor of gamma, then even if you do an infinite sum, if each of the rewards is upper bounded by $1, then the maximum value that the sum can take is a 1 divided by 1 minus gamma. Okay, for let's say gamma being positive. So it's going to be some, let's say gamma is 0.9, then there's going to be at most $10. So that's shorthand is just the summation. Okay, this return random variable we are describing only because we'll see how that is related to directly defining what is called a value function. Okay, we saw value function earlier as the value of being in some state, right, under a policy. But here no policy yet, but still we can define a value function. Okay, because everything is autonomous. So we don't have to do anything. The state sequence realizations are already determined in the transition probability matrix, and the reward function already tells you what rewards you're going to get, And so if you're just summing up numbers, so this GT is essentially related to the value of being in state. Okay, so the value function, which is the long-term value of being in a state, you can just, this is the English interpretation of what V of S is. V of S is nothing but the expectation of this random variable, given the starting state is little less. So here the starting state is not specified, so we're just going to say, hey, given the starting state, which is st is equal to little s, tell me what all can happen in the future. So given little s, maybe the next state is some s prime, the next state is some s double prime, and so on. Because the next state is s prime, maybe some reward got realized. Because of double s prime, some reward got realized. You're just averaging them out. Okay, so you're just adding them up. That's some random variable. So if it's a random variable, it can take many different values. So you're just averaging it out. Okay. So this expectation is actually, is deceptively simple in the sense that this expectation is with respect to randomness in the reward. This expectation is also with respect to possible states that you can go, right? So if you think of a potential 10 length state values that can realize, there could be many different trajectories, right? Trajectories as in state values. So all that is hidden in this expectation here. Okay. But it's just an averaging of what all can happen in the future. And based on that, what is the discounted total reward that I can get, okay, on average. So that's the value function. So these are like static numbers you can compute if somebody tells you the specification of the MRP. So if somebody tells you, hey, here's the state, here's the transition probability function, here's the reward function, here's gamma, just tell me what the values of the states are, you can just compute it. Okay, so because you can just use those, use some techniques because you know the distributions, transition probabilities and things like that, you can just compute this. Okay, that's a pure computation problem. So, but what we want to see for this is actually with the MRP process is that there is a recursive relationship that value function satisfies. Okay, so yeah. So let me come back to the slide in a second. Yeah. So the recursive relationship is as follows. Okay. What is meant by recursive relationship, right? So here we have a function, okay, which produces one number per state value, right? So if you look at this one, there's 1, 2, 3, 4, 5, 6, 7 states, right? So 7 numbers that I can produce. The V of S is S can only take 7 values, 7 inputs, so 7 outputs, right? So there's 7 numbers V of S. V of S is basically what this recursion idea is just saying that each of these V of S number is related to other V of S numbers. So these 7 numbers are related to each other is what we're trying to say. Okay, so what is the recursion here? It's just saying that V of S, which is just the expectation of the return random variable given starting state little s, is related to V of some capital S random variable. So this is a capital S random variable. If you wanna, if you take the expectation, it's basically V of S's at different some other state values. That's all. Okay. So for example, let's come back to here. If you're in class 2, you can only go to class 3 and sleep, right? So which means here V of class 2 being class 2 is related to V of sleep and V of class 3. That's all it means. Okay, and so there's some averaging because hey, with what probability will I get to class 2? With what probability will I get to sleep? That's what's going on with this averaging. Okay. So this recursive relation, although there's a bunch of equations, all they're doing is put up the definition of GT, which is just this series. Okay, the series sum here, and take gamma common so that you have RT plus 2 plus gamma RT plus 3 and so on. And then realize that this summation here, if it's an infinite sum, is also just defined to be GT plus 1, okay, with a gamma in the front. And then from second last step to last step is just that noticing that you can, so this, remember this expectation, as I said, hides a lot of, basically hides the transition probability distribution and the reward random variables distribution. So you can actually push that expectation inside because expectation is a linear operator. So expectation of x plus y is expectation of x plus expectation of y. So you can push some of the expectation operation here, and so g becomes v. Remember, v is equal to expectation of g, right? So that some expectation can be pushed in, and that when you evaluate it, it becomes v. Okay. So, but for us, it's not the derivation which is important. The important thing is the value of a state is related to value of other states. Okay. that's not really mind-blowing, because all of them are related to each other, because all of them are just looking at how many rewards can I get from that state onwards, right? So of course, if you can think of value of if you're in one state, you might go to the second state, and from there you're going to getting rewards. Of course, the values may be related. So intuitively, at least, it makes sense, right? So this recursion will be important in deriving the Q-learning algorithm. Yeah. Yeah, that's how it is to discount, right? You have to discount. Discounting function is there's a power of gamma here. So the time value of reward. We are discounting the reward in the sense that we're just, if the reward is $1, we're just discounting that, hey, today still I'm in state ST or whatever, I'm in time index t. The reward I can get 2 time steps from now is gamma square times $1, for example. So it's not valuable to me as much as a reward right now, for example. Here is a completely autonomous system, so it's just the gamma is there for technical reason, which is just that some things have to sum to less than infinity. But yeah, we are discounting dollars that we get in the future. If you think of t as a time index, okay. We don't have to discount in some other Markov chains where, for example, there's a fixed time horizon. Okay, so I guess, in fact, fixed horizon is the name that you can search for if you want to look up. So there you don't need to give gamma, because if you have fixed horizon, there's a fixed sum of numbers. As long as each reward is upper bounded, then your dollar values, your rewards are not going to blow up, right? So for those problems, you don't need this. We just took a, so I'm hiding some details here. We just took a infinite horizon. So whenever I'm describing things, these are infinite horizon versions. Okay, so that's why there's a gamma discounting factor. Yeah. Yeah, so this slide is just showing, hey, if I add an attack on a reward, again, it's completely, this whole thing is autonomous, right? As I said, we don't do anything, intervene yet. And so every time you reach a state, I can just put a reward, hey, there's a reward of -1, -2, +1, whatever. And then, according to the states that are getting realized, state values that are getting realized, there's going to be an appropriate rewards that are going to get realized. And then I'm just computing the G value according to those rewards. Okay, the G value is going to be, with a discount of 1/2 for the next guy, with a discount of 1/2 square for the, 2 guys later, and discount 1/2 to the power 3, and so on. Okay, based on that, some realized value of G. Instead of V1, just think of this as G1. Okay, and then average of these guys is going to be an estimate of my value for that state. Okay, so you can see that the value of this state, kind of probably is like 3.2 or something like that, right? Or whatever, 3 or something, -3 or something, right? Whereas maybe, so this is a value of being in state C1. So if you start summing up from, let's say, class 3, maybe you have a higher value because you're closer to, from class 3, you can go to either pub, which is a positive reward, or you can go to pass, which is also positive reward. So maybe your value of being in state class 3 is probably higher. Any questions here? Okay, so this, we're not super interested in this equation, except for, hey, V of S is related to other V of S's. Okay, that is illustrated graphically here. So what we're trying to show is that, I think of V of S for a specific little s as one circle here, that is connected to, in some sense, in the sense which is shown here in the above and below, is connected to V of some S prime, okay, for some other S prime. So each circle here just represents a state, okay, so like S or S prime and so on. So from S, maybe you can jump to S prime, maybe from S you can jump to some other S prime. Like, for example, we saw with class 1, you can either go to Facebook or class 2. So think of this as class 1, and you can go to Facebook or class 2. All I'm saying is V of class 1 is going to be related to V of Facebook and V of class 2. That's all. Okay, and all the other terms will kind of are not relevant, because you can only go from class 1 to either Facebook or class 2. So, but in general, you can write an average of all the things that you can reach from given state, and then their values. That's what's happening here. Okay, and and with a gamma discount, and the immediate reward that you can get from being in the current state. So the bottom equation and the top equation are the same, actually. It's just written in a slightly different way. Okay, so if you expand out this expectation of reward, we remember it's just script R, and then expectation of the this value function is just the all the states that can happen for the random variable here, st plus 1, which is all s primes that you can reach from S. Okay, so now let's talk about Markov decision process. Took a long time to recap, but this is where we wanted to start. This is where we left off actually last time. Here we left off, and we wanted to discuss Markov decision process. Okay, so Markov decision process is a Markov reward process. It's just a reward process with an extra element, which is that now the system is not autonomous. Every time step going from at a given time step going to the next state can be influenced by an external factor, which is the action. Okay, so that's the only extra thing. So for that we need to have an set of actions. So that's the set of actions is script A, so action space. And then the transition is influenced by action. So it's not just, hey, you can go from st to st, which is little less, to st plus 1 being s prime. This is also influenced by the action that you took at time t. So that's the extra term. So that's why it's in red. Similarly, the reward, need not be just the reward associated with each state, but it's basically reward of being in a state and taking action A. That is what generates a reward here. Okay, and everything else is the same as before. Okay, so that's the definition. So here, so you must say, hey, how is it related to reinforcement learning? Because we started reinforcement learning. How is now we're talking about some very specific objects, which are generally represented as these tuples, like state, transition probability, reward, gamma, or state action, transition probability, reward, gamma. This is just a definition of an object. Okay, just think of a Python class with this definition, and then all you're trying to do is, for example, for Markov reward process, you may want to get, hey, what are the values? Okay, so what are the values of different states, right? So for which you need to solve the system of equations. Okay, so actually this is just a system of equations. If I tell you R, if I tell you P's, then it's just a right hand side is just a linear equation, in fact. Okay, so all you're saying is, hey, can you tell me the values of states? Solve the system of linear equations. Okay. Other than this, I don't think you can do much with Markov reward process. On the Markov decision process also, you can do something like that, right? So you can estimate the values of states given all this tuple information, like all the transition probabilities, rewards, and so on. Or you can do other things, and we'll see what the other thing could be. In fact, we can learn a policy, because that's the extra factor here with the thing in red. There is some actions that we can intervene with. Then the question becomes, hey, what is the best set of actions that we can intervene with? Okay. So let's do that. So for that, this diagram is a different diagram than before. Okay, although it has the same names like Facebook, study, and all that. But now I'm kind of dropping names for the states themselves. So if you look at the circles, inside the circle, there is no state value, okay, because that's not going to be relevant for giving this example. So what's happening is I'm thinking of these Facebook as an action. So if you're in some random state, okay, some specific state value, if you take a Facebook action, then you'll go to some other state with some reward. If you take a study action, you're going to go to some other state with some reward, and so on. Okay. So these things in red are now the actions. Okay, that's why they're in red, and everything else is the same as before. Okay, so if you take for example, here in this some state, you can either study and go there, or you can take a pub action and go here. Okay, so why is this thing, the bottom thing in dark, is not a white circle? Is because there's no action being taken there, in the sense of irrespective of what action you do, you will end up either in study with some probabilities, which are the probabilities are 0.2, 0.4, and 0.4. Okay, so it's just no action is needed, or you can put an action, but it's kind of irrelevant. Okay. But here, note that if I'm in this state and I take a study action, I'll deterministically going from that state to the state. So there's no stochasticity in terms of if I take that action. At least in this illustration, there is no randomness in terms of if I take that action, I can go to some other state. It's just not happening here. Okay, it's just a illustration, limiting illustration, but I just wanted to show that. Okay. Any questions here? Okay. Yeah.
How does MDP relate to HMM? Is there any transition?
MDPs are related to hidden Markov models, in the sense that hidden Markov models are also about random variables. Okay, so hidden Markov models also have a bunch of random variables, observation random variables, as well as the state random variables. The state random variables are hidden. So I would say hidden Markov models are, the connecting point would be Markov chains. Okay, so something like a Markov chain would be kind of something that you would see. Sorry, this Markov chain, for example, could be the hidden state of a hidden Markov model. What you observe could be maybe time spent or location or something like that. Okay, for example. So of course, given location, you can figure out what the hidden state is and so on. But all I'm saying is hidden Markov models, of course, are related to Markov chains. Okay, because by the name Markov there. But hidden Markov models are about each state itself generating some extra random variable. Okay, realization of another random variable called an observation random variable. That's not there here in this discourse, what we did talking about today. But Markov chain is the current connecting core, I guess, idea there. Okay, for both hidden Markov models and here. Okay, but HMMs don't have actions or rewards and so on. So that's why I guess the later enhancements that we did, like MRP or MDP, they are not that related to HMMs.
So in MDP, do we have emission matrix as such?
We don't have emission matrix, but you can add an emission matrix if you want. Okay, so in Markov decision processes, there is no emission matrix as such. Yeah, there is no explicit treatment of an emission. You can add it. Okay, it's going to be some variant.
Actions are also stochastic.
There is no actions in HMMs, right? There's actions here. Yeah.
So they are stochastic and they must have.
No, they don't have to be stochastic. If I'm an agent, so if I want to, so somebody has to describe what actions to take in each state. That person can describe the state actions to be deterministic as well. But in general, yeah, they can be stochastic. But somebody has to supply that as an input. Okay. We'll talk about that action part, which is the focus for that. You know, we'll talk about that. In fact, right now. Yeah, we'll talk about actions in a second, but they're not related to observations, right? In the hidden Markov models, it's not related. Yeah, I don't see further connection, I mean, to any comment, but we can discuss it during the break or offline. Yeah.
And the rewards here are dependent on the state, not action.
No, now they are dependent on actions, right? So because the rewards are now closer to the edges rather than the circles. So here it's just saying that if you're in the state, if you take the study action, you can only do one thing, which is go to the next state. Okay, you can only do one thing, which is go to a specific next state. Right? In the general description, I said if you're in some state, if you take an action, there's some randomness with which you can go to some different states. Okay, so for example, if you're in state leftmost circle here, right? This circle here, take the red action, study, then this is saying, hey, with some probability you'll get to some circle, like this circle, with some other probability you may get to some other circle. Here it's not showing that, because here every state, if you take some action, you're only going to one next state.
So it depends on action and state.
Yeah. So here rewards are depend on both state and actions. Okay, this is a very degenerate example, corner case example, just to kind of keep it consistent with the previous examples. But yeah, rewards can depend on both state and actions. Yeah. Okay. So now that we have introduced actions, then we can now start talking about policies and how do they influence values, right? So clearly, again, a policy is just a distribution of actions given state. So it's just the probability of taking action little a given state little s. Okay, so that's y of a given x. So more generally, for finite horizon problems, generally what happens is this policy also has a time index t. Okay, and the reason why this infinite horizon version of it, the gamma discount, is what we're talking about here, only because then we can kind of focus on what are called stationary policies. Okay, basically policies which don't have a time index. Okay, so here you can see that whether I put a t plus 1 given st plus 1, or whether I put a t and st, it's the same. It's not dependent on time. Okay, what action you take is not dependent on time. Okay, it's just a it's just a discussion point here. It's not a big limitation in the infinite horizon versions that we're talking about with the gamma stuff, where this makes sense. Okay, this distribution, this policy makes sense for finite horizon situations. Like, hey, a game can only last for 30 minutes, or a game can, or some decision process can only run up to 10 minutes or whatever, 10 days. Then your policy may be dependent on, hey, how close am I to the end? Because then if you're too close to the end of the horizon, maybe you may want to be more risky, or I don't know, like you may do something different. So time may be an important feature as a part of your state. Okay. Of course, time can be part of the definition of state itself. Then whatever I said is kind of is also covered in that. Okay. So remember, states are indexed from 1 to n, but you can also think of state as a vector. Okay, it's like a state vector or feature vector or something. Okay, so you can always include time in there as a feature attribute. But yeah, so anyway, policy is just a distribution of actions. It defines the behavior of an agent. Okay, so what the agent is doing is in the MDP object, the agent is, think of the MDP object as a definition of your environment. That's what essentially it is. If you want to do RL, then you can say, hey, somebody can define the MDP, and then I, as an agent, I'm going to keep interjecting my actions, send the actions, and the MDP class or whatever the object created from the MDP class can keep sending me the next states and rewards. Right. So MDP is essentially a simplified definition of the environment. The environment can be quite complex, like in real world or elsewhere, even in simulators. But from the agent's point of view, they can say, hey, summarize the environment MDP if they want. Okay. To summarize it, of course, they need to know what the all possible states are. They need to know, of course, what all actions they can take. That's fine. But they also need to know the transition probability matrix, or an approximation of that, of what could approximate the reality or the environment. And they also need to know the reward function, which also could approximate the actual environment. Okay. So, but if you learn all this, then you're basically learning the model of the environment. Okay. So now you have a model, and still you're trying to decide a policy. So an agent could learn a model of the environment and then take actions. Okay.
That policy is based on optimization.
Yeah, which we are not talking about at all. So there's only one algorithm we'll see of how to get to good policies, how to get a policy. Yeah, we're going to determine. So if the problem is offline, so if it's just an MDP and we're not, an MDP is completely specified, like state, actions, transition probabilities, rewards, and gamma, then obtaining a policy is just an offline optimization problem. Okay, is an optimization problem, and we'll see that in a couple of slides. When we tie it back to RL in a few more slides, then there it's not exactly an optimization problem, because we have to learn how the environment, what the environment is. Even if the behind the scenes the environment is an MDP, we don't know the numbers of the, we don't know the parameters of the MDP, and so we still have to learn something. Yeah.
So where does Bellman equation come into?
For both, it's a Bellman equations are used to solve the offline optimization problem. They also inspire some algorithms, and one of them is Q-learning. Okay, so Bellman equations are used. We'll see Bellman equations in a second. Okay, so first observation is that an MDP is nothing but a Markov reward process for a fixed policy. So if I tell you the policy pi, okay, some policy, somebody just gave an input, hey, in every state take this action, or in every state this is the distribution of actions. If someone tells you already, then the MDP is just nothing but, again, a passive thing. Okay, some states jumping from one state to the other, because I've already told you what action to take in every state. So everything is kind of predetermined, and rewards are also predetermined. Okay, so given an MDP like this, and if I already tell you the policy pi, then the state sequence is just a Markov process or a Markov chain. Okay, what is a Markov chain? It's according to this. Markov chain is just a collection of states and a transition probability. So here the transition probability is denoted as p to the p superscript pi. Just to note that under the policy, this is a transition probability kernel. Okay, this is going to be derived from the original p of the MDP, in a very simple way. We'll see that in a second. Similarly, the state reward sequence, state, this is the reward, next state, this is the reward, and so on. It's just a Markov reward process. Again, state, p pi, r pi, and gamma. So p pi and r pi are just some derived transition probability functions and reward functions. Okay, so what are they? It's a simple here. So what we want in a Markov process is, what is the probability of going from state S to S prime? That's what we want. But what we have in an MDP is, it says, if you're in state S, if you take action A, where will you go? So there's some extra information. So you need to average it out. So that's what's going on. So it's just saying, if you give me a policy, then I know that according to the policy, if I'm in starting state little less, then there is some probability I'll take action A, there's some probability I'll take action some A prime, and so on. For each one of them, there's some probability with which I'll go, if I take that action, I'll go to S prime. So it's just saying, hey, find all the ways you can go from S to S prime, mediated by actions. Okay, so if I take action A, maybe there's some probability I'll go to S prime. Maybe I'll take action A prime, there's some probability I'll still go to S prime. Then just add them up. That's the P pi of SS prime. Okay, it's just there's just a bit of a warm up. It's not a really hardcore fundamental thing going on here. It's just a observation that if you given an MDP and somebody already tells you a policy, then it's just a Markov reward process. So it's a completely autonomous thing. You can just compute things. Okay. Similarly, R pi of S is nothing but averaged out, what all actions you can take from little less, and then average out the rewards that you can get because you took those actions. It's just an averaging procedure going on here. Okay, so that was one observation, and because we said given a policy, we just get a Markov reward process, and for Markov reward process, we already defined a value function, right? We define a value function, and we also saw the recursion. So we can also talk about value functions here, right? So which I guess here, the formal, I guess, full name is state value function, okay? Because we're going to distinguish it with some slightly different value function in a second. The state value function V pi of S. So remember, there's a subscript pi, which means that I have already told you the policy. Therefore, it's an MRP, and therefore, if it's an MRP, it's just the expectation of the return random variable according to the policy pi. Okay. So what is this policy pi doing? All it's doing is removing the degree of freedom. So remember, there was an A that we could have in every state. We could say what was A. Pi is already telling you what is A, because pi is saying in the state little less, you should take action A. That's a policy, right? So therefore, we have lost the degree of freedom. So it's completely autonomous now. Okay. So this expectation with respect to the policy, the dynamics of the system, and the reward randomness, and so that's the expectation. That's what the expectation is going on here, and that's the definition of the state value function. Okay. So this we have seen for MRP, so it should not be a big leap, except for the extra subscript pi. The second thing that we have not seen is a slightly related function, which is going to be useful for us to talk about, because it's a function that's something that is essentially what gets estimated in Q learning. Okay, so just to give you a teaser, this is the function that we'll estimate in Q learning. Okay, so what is this function? It's called the action value function, or the state action value function. Okay, it's just the same. It's a function which is very similar to V pi of S, except it has a second argument A. Okay, second argument A, and so it's just saying what is the expected return starting from state S, but not immediately applying pi, the policy that I have already been given, but just take 1 degree extra degree of freedom, that the immediate action that I'll take is something I can control as an input, but right after that I'm going to keep applying pi. So it's just delaying when you can apply pi. Okay, so it's just leaving out, hey, for the first step, just let me take as an input what action to take, but from the next time step onwards, it's just going to apply pi. Okay, so it's just the expectation of the return random variable, except that the starting state is the same, a little less, but the starting action is not according to pi, but according to some input. Okay, some like an arbitrary action little a. Okay, so this is called a state action value function. So how is this Q pi of S comma A related to V pi of S? If you take this A, little a input as just pi of little s, okay, then there is no difference between these two. Okay, so if you already, like, even the first action, like even the input action that you can give is exactly the action that the policy would take, then Q pi of S comma pi of S basically is the same as V pi of S. Okay, there's no difference actually. It's just that we are freeing out 1 degree of freedom, like not applying the policy immediately, but like applying the policy 1 step later. Any confusion? Less, for simplicity, if you want to think about it, you can think about deterministic policy. All this discussion applies to stochastic policy as well. Sorry, but you can think of it as a deterministic policy. It makes it easier for you to understand what's going on. Yeah.
And how does the policy look? Is it a sequence of steps?
No, policy is a function which so think of a table, a lookup table. Policy is a function. Every state, what to do. Every state, what to do. It's a function.
That can be deterministic as well as.
Yeah, it can be deterministic or stochastic. Yes. Yeah. I mean, in the previous expressions when I did, I was showing stochastic versions, right? So here, this is a stochastic policy, right? But if it was a deterministic policy, there would not be some summation like this. It will literally say, hey, pi of s here. Instead of a, you could have just written pi of s, and it'll just say exactly in that state, hey, do exactly this action. So there's no need to even talk about any further averaging, because I know exactly what action I'm going to take. Yeah, if you want to think of policies as deterministic, that's fine. Okay, not an issue. The only new thing here is that difference between state value function and state action value function, or the action value function here, is that it's just taking a second argument. And the second argument, if you just take the second argument as pi of s, then you don't have to do, this is the same as v pi of s. But because of second argument, you're just saying that I'm going to apply the policy second time step to one time step onwards. Okay? So first time step, I get to, you can tell me what action to take. Okay, so this recursion that we saw for value function from Markov reward process is exactly called Bellman expectation equation. It's called it's called Bellman expectation equation. That equation also holds for q pi of s comma a. So v pi of s, we already saw this recursion. Okay, it's just the expectation. Given the policy is just a Markov reward process, we just saw that it's just immediate reward plus gamma times the next states, states that I can reach to and their values. Okay, this one we saw before, except that now we have an extra subscript pi just to denote that under this policy. Right. Similarly, q pi of s comma a has the same, recursion. So it's q pi of s comma a depends on, is related to other q pi of s comma a's. Okay. In this way, so it's just immediate reward, starting from state st is equal to little s and taking action little a, immediate reward that you get, plus gamma times whichever state action pair values that you reach, whatever probability that you'll reach, their averages, basically, their averages. Actually, there's a diagram in the next slide. Okay, let's just, we did this for the Markov reward process just to kind of relate what's going on. So here the diagram is a dark dot represents a state action pair. Okay, a circle still represents a state, okay, as we saw in the previous diagram like this. Okay. So it's just saying that a dark dot, which is a state action pair, there is some number associated with it, which is q pi of s comma a. That number is related to other q of s prime a primes. Okay, so some other q values at different locations. Okay, that's all it's saying. Okay, and that can be, this is exactly what the recursion equation is, or the Bellman expectation equation is. It's just saying that the state action value at a given state action pair is related to other state action pairs. Okay, of course, you have to, if you're in the state and action, with some probability you will go to state s prime, with some other probability you may go to some other state, right? That's according to transition dynamics. And then at those states, if you take action a prime, you may get to, you'll be in this joint pair s prime a prime. There'll be some number. If you take some other action a double prime, you'll be in some other joint pair s prime a double prime, and so there'll be some number associated with that. And so these numbers here, q pi of s prime a prime, are related to q pi of s comma a linearly. Okay, again, a system of equations which are linear equations. If you think of this as a variable, then kind of variable relate very similar to them are there on the left hand side. Sorry, on the right hand side. So this relation, this graphical diagram, or this last equation here is expanded out as q pi of s comma a is the immediate reward plus gamma times all the states you can reach for a given starting state s and taking little action a. Those were two inputs. These are the probabilities with which you can go to those s prime states. At those s prime states, you get to choose some action according to pi. Okay, so at s prime state you can take action a prime, a double prime, and so on. All those things can be again averaged out. Okay, so there's a double averaging going on because your policy could be stochastic here. That's all. Otherwise, it will be just one averaging. If this policy is deterministic, then there'll be only one summation here, which is all the states that you can get to, state values you can get to. So this is Bellman expectation equation. Why is this? So this is basically giving you a sense of, forget about reinforcement learning problem. If somebody gave you an MDP, okay, somebody gave you an MDP and told you, hey, here's an MDP, here's a policy, tell me value function, tell me the state action value function, then you can just solve the system of equations. Okay, what is unknown is Q. What is known is somebody go with the policy. You already know the MDP, therefore you know the P's, you know the R's. Okay, so you just need to solve the system of equations. Okay, so it's just a pure computation problem. Okay. Now let's come back to a slightly different problem that we can frame, which is now saying, hey, I don't want to give you a policy. Tell me what the best policy for this MDP is. Okay. Now it's a slightly different question. Previous question was given an MDP under policy, tell me the value function or state action value functions. Okay, so you can just solve some computation. Here the question is given the MDP, tell me what the best policy is. Okay, so for that to define best, we can define best in a couple of ways, but they are all the same. Okay. One of the ways is via the state value function directly, or we can state in terms of the action value function. Okay, it's basically both of them are equivalent. So let's just focus on the bottom one. It's just saying we're going to define Q star of S comma A as the maximum that Q pi of S comma A can reach when I optimize over pi's. Okay. It's a very pretty complicated thing to imagine, like, hey, how do I keep changing pi and how does Q change? But there's a succinct notation to just say that, you know, different pi's will lead to different Q values, and there will be some Q value will be high, you know, highest. What is the pi that corresponds to it, and what is the Q value itself? Okay, the Q value itself, let's call it Q star. Okay, so that's the objective. So we want to, you know, what the objective of, you know, when I say objective, sorry, what I mean is if you've been given an MDP and somebody tells you doesn't give you a policy but asks you what is the best policy, then essentially they're asking for, hey, find a policy that maximizes the Q values, for example. And you can see that the Q values here are specific to a given state and action, but that is actually not a big deal, in the sense that whether you start from S and A or you start from S prime A prime, it's just, you know, you may see it will be a different optimization problem, but they're all will lead to the same policy. Okay, that's just a side note. That's because we are in the infinite horizon setting, so the starting state action pairs really don't matter for this optimization. But yeah, you can always keep the starting state fixed and say, hey, given this starting points, tell me what's the best thing you can do. What's the best policy you can come up with? Okay. Now we are optimizing our policies, really, right? So here the output has to tell me at every given state, what should I do? So it's a function. So this optimization problem is actually a search over a function space. Okay. So like linear functions or something like that. Okay. So this problem now is looking like a supervised learning type of problem, because you're in the supervised learning also you're trying to learn, for example, parameters of a linear function or parameters of a neural network or something like that, right? Okay, so this star things, which are Q stars and V stars that we saw, let's focus on Q stars. The star objects, star values, okay, they also follow a recursive equation. It's a non-linear recursive equation, and that's called Bellman optimality equation. So what is that recursive equation? Is just Q star of S comma A is related to the immediate reward plus gamma of starting from little s and taking action A, you can get to what all states you can get to, S primes, and then the max of the Q stars at that state S prime. So at that state S prime, maybe you can take 3 actions, then you are just giving what is the maximum of those 3 actions. Each of these 3 actions will lead to 3 different Q star values, which, you know, whichever is the highest, that's the one you plug in here. Okay, so in terms of diagram, we're just saying that Q star, which is associated with the state action pair SA, you can see that SA, you know, if you are state S and you take an action little a, you get a little reward R, you get to some state S prime. At S prime, there could be many actions to take, let's say 2 actions to take. The maximum of them is what's going to be assigned what's going to be important for you. In the sense that the maximum of them is what's going to be useful for relating to the previous Q star. Okay, so of course there's going to be Q star S prime A prime here. There's also going to be a Q star S prime A double prime here, for example, for this guy. But the maximum of them are what relates to the previous one. Okay, so it's a non-linear recursive equation. Non-linear because there's a max here. Okay, now you may say, hey, how did we get here? That we will not discuss because that. Why does Q star satisfy this particular expression is something beyond the scope of our discussion, but it's just a fact for us for this at least for this discussion, that Q star satisfies a nonlinear system of equations. Okay, so again, if somebody asked you, hey, here's an MDP, tell me what the best policy is. Okay, I will get to the best policy, but let me do it via the route of finding Q stars. If I want to find Q stars, I can just solve the system of nonlinear equations. Okay, so where Q stars are known, so like some bunch of variables, but I know the R's, I know the P's, and I don't need the policy anymore here. And so I can solve the system of linear equations, system of nonlinear equations, because there's a max here. And then I can compute some Q star. Okay, so let's say I compute Q star by solving the system of nonlinear equations. Then from Q star, I can compute a policy and then report that back. Hey, here's the best policy you can do for this MDP. Okay, I can tell you what I'll tell you what the relationship between Q star and the policy is, which is in the next slide. Okay, which is, if once you have Q stars at every state action pair, then remember policy has to say at a given state what should I do, right? What action to take. And in fact, it turns out for this class of infinite horizon problems, the optimal policy is actually a deterministic policy. Okay, it's not a stochastic policy. And the optimal policy is saying, hey, if you're in a given state, maybe I have three actions to take. Whatever action leads to the highest Q star, that's the action I want to take in the state. Okay, so I'm defining the policy based on Q stars. Okay, and this is what I'm calling as the best policy. Okay, and this is actually, it's just the, if you remember, we were showing the Q star is the max of something. Argmax of that would be pi star, right? So pi star would be the policy that maximizes this thing. That pi star is exactly equal, if you know Q star is just going to be argmax for in every state, take the best action based on Q stars. Okay, that's the relationship between state action value function and policy, the best policy. Okay. So this is how you would solve an MDP problem. If somebody gives you an MDP problem, it may not be related to reinforcement learning. Somebody tells you already state actions, next state actions, transition probability, reward function, gamma. Then you can just do computation. If you can solve the Bellman optimality equation, and then you get some Q star function basically, and then using Q star, you can just say, hey, here's my policy. Okay, but it's not so easy. What I'm hiding here is that if you think of system of nonlinear equations, this is depends on the number of states and number of actions. If you have 1,000 states and 1,000 actions, already you have like a million equations here. Okay, and you can imagine you may have more than 1,000 states. You don't have to have 1,000 feature vectors, right? You can have infinite number of feature vectors. And what do you do? So we'll discuss about those things a little bit later today. But if you could solve the system of nonlinear equations, you can actually solve the MDP. Okay, but now we'll slowly come back to our reinforcement setting where the MDP is not specified. We just have an environment. The only thing we can do is our API or interface is we can only send an action, we can get a reward and the next state back. That remember from the first part of last lecture. So given that, we need to still learn the best policy. Okay, I mean, in the sense that we need to learn the best policy only because we want to maximize the total expected reward, and that can be achieved by knowing the best policy, or at least doing actions which a best policy would do. Okay. Any questions here?
What would happen if the MDP is infinite? So
Number of states is infinite, you mean?
So how will the optimal policy look like?
For infinite state spaces, our discussion doesn't hold right now. Actually, that's not true. So it's just that these equations may hold. Okay, these equations are not really talking about whether you're finite or not. Although here I'm summing up things. Instead of summing up things, you may have to do an integration. Okay. So these equations may hold, but solving would be a harder problem. Okay. Solving for the best policy would be a harder problem. So for infinite state spaces, solving an MDP is beyond the scope of our discussion right now. Yeah, but the Bellman optimality equation and Bellman expectation equation nothing to do with finite state space and finite action space. Of course, this max will become a I mean this max on an infinite set can sometimes be achieved or not achieved. So sometimes people write infimum or supremum and things like that. But what I'm trying to say is that equations hold, but how to computationally do it on a computer? For finite state spaces and finite action spaces, you can just try to solve this at least. And I'll talk about how to solve it, okay? You don't have to directly try to solve for the system and nonlinear equations in one go. There is an iterative approach. In fact, it's called the value function iteration, okay? It's just literally called that, the algorithm is called that to solve it, okay? But that iteration still requires finite number of states. Okay, so the infinite state space extension we are not discussing here. Yeah, but it's doable. It's just beyond the scope of our discussion. Yeah, but so in general, solving MDPs offline is a hard problem. Okay, is a hard problem because of this nonlinear nature here. You don't have to solve it via this. Okay, you can solve it in any other way. All you need is somebody tells you here's an MDP. Give me the best policy. You don't have to do it via Bellman optimality equation. You can try some other ways, whatever ways you want. But in general, it's a pretty hard problem. So a lot of researchers still continue to figure out better and better ways to just solve that optimization problem. It's just a computational problem, okay? But computational complexity, how to do it in an efficient way for complex situations, complex domains, is still a research question. But we know some algorithms do it. It's just that those algorithms may be super inefficient for some applications. Okay. Any other question? Okay, let's take a break for 10 minutes and then resume at 5. Okay, so welcome back. So what we'll do next is start looking into the Q-learning algorithm. Okay, so now we have basically the baseline infrastructure to start talking about some solution techniques, and we'll only look at one, which is Q-learning. So okay, so we are back into the so we are going to be back into the RL setting, but we'll also briefly mention something about the MDP setting. So for our context, just to kind of differentiate what is slightly different from the MDP setting, what is the slight difference between the MDP and the RL setting? The difference is that in the MDP setting, think of somebody telling you state, action, transition probability function, reward function, and gamma, and then just asking what is the best policy. That would be the MDP setting. That's slightly different from the RL setting, where we want to collect total rewards. We want to kind of maximize collecting total rewards by figuring out a good policy, like what actions take in different states, where our interaction is only via an API, which only doesn't which only lets us send an action, get a reward, and next state back. Okay? So it's an online setting really. So RL is just an expanded version of contextual bandit or an expanded version of multi-arm bandits, right? Whereas the MDP setting is there's no online interaction. Somebody sells you MDP, it's literally them telling you, what the state transition probability is and what the reward function is, and so you can use and, for example, solve the system of nonlinear equations that I mentioned to figure out the best policy. Okay, so it's just the online nature and in the feedback loop, which is different. Okay, so you don't know anything, so you have to learn and take actions. Okay, very similar to MDP or the contextual bandit settings, where you want to learn what's good and what's bad, and then therefore take better and better actions adaptively, okay, as time progresses. Okay, that's the difference. So what are the ingredients needed to find the best policy? First thing is you should be able to evaluate the quality of a policy, right? So forget about finding the best policy, if you can't even evaluate how good a existing policy is, then you are in a bad situation, right? So for a given policy, you should be able to say what is the q pi of s comma a for that policy. Okay, let's say s comma is like some starting state and some fixed action that you're taking, for simplicity at the beginning, and then from then onwards, if you apply the policy, hopefully you're getting high rewards. So that's exactly captured by q, right? So q is the expected total reward. That's why we're maximizing it. I don't know if we missed that towards the end when you're saying max of pi of q pi of s comma a. Exactly q pi of s comma a, because it is exactly the maximize is the expected total reward. Okay. And sometimes we also have to do control, and that depends on whether you're doing an iterative. So of course, estimating for a, so if I can estimate the quality of every policy, then I can say, if I could enumerate the policies, if there are only 10 policies, then I can estimate for the first policy, estimate for the second policy, estimate for the third policy, and then figure out which one is the one which is maximal, which has a maximal q pi of s comma a, right? But the policies may not be finite. Then you will have to do some control in the sense that somehow figure out how to go from a policy to a better policy. Okay, that's, I guess we're just calling it as control. Okay, so prediction just means like estimation, like estimate the quality of a policy, and control just means, hey, how do I improve from an existing policy to another policy? Okay. We will focus on the RL setting mostly. I'll briefly just mention the MDP setting. How do you get the best policy? But I've already mentioned a couple of times, how do you get the best policy for the MDP setting? You just literally solve the system of nonlinear equations. That's one way. We'll focus mostly on the RL setting. And so remember, RL is again just interaction via next state reward being given back to you if you tell me what the state is, what the action is. Okay. So we'll focus on RL setting, and one of the algorithms there is called Q learning. Okay, so what it does is does both. Somehow get a sense of what the quality of a policy is, and also it makes an improvement. Okay, and so we'll see how it does that. Maybe not exactly in these two buckets, but we'll see how it learns. Okay, so here, and so we'll start with the mechanical procedure itself, because it's kind of relatively simple to state, and then we'll kind of spend a little bit of time trying to understand what each of the steps in that procedure are doing. Okay, it's a procedure very similar to UCB1 or Thompson sampling and so on. So there's going to be iterative as a function of times. There's going to be a for loop basically, and each time step we're going to do something. Okay, so what we start with is because we want to learn the Q function, as the name suggests, it's a Q learning algorithm. So it will learn the Q function. Q function is a function of both states and actions, right? So since it's a function of two variables, and for simplicity, we're assuming that the number of states and number of actions is finite. Okay, so you can really think of that function as a 2D matrix, right? It's a matrix where if you index a state, index an action, there's a number, and that's the function value, right? So I think this should not be very surprising. If you have a one-dimensional function with a finite number of inputs, then you can literally think of it as a lookup table. So here it's a lookup table with 2 dimensions. Okay, number of states and number of actions. It's a matrix where each cell represents the Q value for that state and that action. Okay, so you start with a table. Start with some random numbers if you want. And let's say we are always starting at the starting state. Let's say we're starting at starting state S1. Okay, some specific value of the state, and then for every time step we're going to do something. Okay, so if you recall from our previous lecture, we said there's one extra thing which happens with RL setting, which doesn't happen in the contextual binary setting or the multi-on binary setting, which is that multi-on binaries as well as contextual binaries, they have to do exploration and exploitation. Okay, we saw the epsilon greedy, for example. Sometimes you have to do some random action, and sometimes you have to exploit what you already know, right? So the exploration trade-off is always there. We have to do that. In addition to that, in the RL setting, you may have to trade off doing a worse action now, slightly worse action now, as in like trying to get a little bit less reward, immediate reward now, for a potentially high reward later on. Okay, so there's a temporal aspect as well, because it's not IID. Every next state depends on what you do now. Okay, so the Q learning algorithm does the following, right? So it's kind of keeps maintaining at every iteration a Q table. Okay, in the sense that basically what we're going to do is keep changing the entries of this table, and this single table, Q table, hopefully after several iterations, this Q table will look like, every entry looks like Q star. Okay, that's what we want to remember. We want to get to Q star. Once you know Q star, we can always say what is a pi star. We had that mapping right before the break. So what does it do in every iteration? Based on the current Q matrix. Okay, so one with some probability it randomly chooses an action that is feasible in this state, in this state. Okay, so maybe in every state every action is feasible for simplicity, let's say. Then just take a random action with some probability epsilon. This is exactly the explore step of the MAB or contextual boundaries that we saw two lectures ago. Or because we are in some current state ST, which means that we look at a row of this Q table, there's a bunch of numbers, one of the numbers is going to be the highest. What action does it correspond to? Just play that action with some probability with the remaining probability. So it's exploring versus exploiting. Remember, this is exactly what you would do if you had Q star. Okay, if you had Q star, you would just take the argmax at every state and you just call it pi star, right? So here we're just doing something similar. We're just saying we are just exploiting. Okay, so if we have, so with some probability we take a random action, with some probability we take the most promising action so far, which is determined by the Q values, the current table's Q values. The current table is not Q star. The current table has some potentially noisy numbers or whatever, some completely incorrect numbers also. That's fine. And so for that we'll do a fix, which is exactly, now we have to update. So once we take an action, we do get a reward back and the next state back. So two things we get back. Remember, that's the API, that's the interaction protocol. With those two things, we're going to do an update on what? On what we're going to do an update is on a single cell of this Q function. Okay, we're only going to modify one cell of this Q table. With cell, the cell where we did an action. With cell is a cell where we were in a certain state and we took a certain action. So okay, that cell we're going to change it. Okay. Now why it's okay. So the update is as follows. We're gonna update the one entry. Okay, one entry in that matrix. That entry is whatever the previous entry is. We're gonna add a term to it. Okay, the term could be positive or negative, but we'll add a term. Okay, and the addition is a weighted addition, so we'll just add a factor like alpha t. Okay, it's equivalent to something like a learning rate, actually, but alpha t is some number like 0.5, for example. Okay. So what is the term that we're adding? It has a name. It's called temporal difference error. Okay, and it's a difference between. So remember, once we played that action, we got two extra things, which is the reward, immediate reward, and the next state. The immediate reward and the next state define this part. Okay, and this part is just exactly what the Q value was before. Okay, at this ST, AT pair. Okay. So it's a little bit weird way of writing because we already have the term here and we are using the same term here. If you want to write it in a slightly different way, it's just 1 minus alpha times the previous value plus alpha times the new value. Okay, it's like moving average, right? So if you're doing a moving average, you do 1 minus alpha times the previous value plus alpha times some new information that you got. Okay, that's how you do a moving average, for example. So that's what we're doing here. So there's an update, right? So previous value with some arbitrary, it's a temporal difference error that is being added. Or you can say there's some new estimate that we computed for the Q value, and this estimate has to be kind of weighted averaged with the previous number that is there. Okay, so that's the Q update, and so we are updating one entry. We'll kind of spend a little bit of time at why this entry makes sense, why this type of an update makes sense in the next few minutes. But if given this update, the algorithm is closed up. It's pretty much done. Right? This is pretty much it. So this is the simplest, I guess, extension to things we saw in the online learning class, a lecture 2 lectures ago. So here there are only two parameters. One is the epsilon parameter, how to trade off exploration versus exploitation, and the second parameter is the learning rates. Okay, this alpha here, how much to believe the old information versus new information. Okay, and the trade-off I was talking about of taking suboptimal actions now for a potential higher reward later, that hopefully is ideally captured by the Q function itself, because remember, if Q is a long-term, it's a value of being in a state. Okay, so if you are in that state, so value of being in a state and taking a certain action. So even if the current action, if you take an action which leads to an immediately low reward, but remember that Q function involves the Q function of going to the next state and potentially reaping high reward. So because the current Q value is a function of both immediate reward and the future average reward that you get, you can potentially kind of take an action which may get less current reward, but may give much higher potential Q values later. Okay, so that's already built in because we are working with Q values and not immediate rewards. Okay, so the problem would be very different if you were just looking at, hey, just maximize the current rewards, right? I mean, then it's just a completely unrelated multi-invariant problem at each state, actually. Okay. So any questions about this algorithm?
Can you explain that again? Why the Gaussian analysis?
Oh, this is just the same as the epsilon greedy part that you have in your. So remember, if you're doing epsilon greedy for multi-invariants, the first two steps are exactly what you do, right? So epsilon is just a way to hedge against the fact that you may not know that a different action would have done better. This is exactly the bandit feedback. The whole, the whole 3 lectures is all about why it's different in supervised learning, right? So every time we take an action, we don't know what would have happened if we did something else. Okay, so with some probability, you want to try something else all the time. Okay, so that's why epsilon greedy or UCB and Thompson sampling and whatever EXP3, EXP4, all of them do that. You see the same pattern here. So epsilon is just some small probability with which you want to try something else because you don't know. You may have a good idea that, hey, the current action is pretty good, but I don't know what would happen if I did something else. Okay, so that's what it's doing. So this first 2 points are just exactly in the given state. The first 2 steps are exactly the epsilon greedy algorithm steps. Okay. Given state, right? It's just the argmax of what is the best thing that you could do given the current state, given with the previous previous estimates that you have, or take a random action. That's with some other probabilities. So the first 2 points are exactly taking action is exactly epsilon greedy. Of course, the only new complication is that how do you update Q? Okay, so how do you update Q? Based on current reward, but also based on what, given the current reward, where would you end up? Where did you end up actually? And there, what was the Q value? Okay, and we'll talk a little bit more about this, why the update is looks like this in the next few slides, but this is the mechanical procedure for now. Okay. Does that answer your question? So we'll answer. So the much of the complexity going on in this slide is more about just this update. Okay, why does this update make sense? This has some connections. I mean, so we'll only make a very intuitive connection, is in fact, for the rest of the slides, and it's going to be related to Bellman expectation equation, Bellman optimality equation, and so on. Okay, but note that 30 years ago, somebody showed that under some assumptions, some theoretician showed that under some assumptions, if you done this for loop long enough, the Q table actually converges to Q star. The Q star would be exactly the little Q stars that we're looking at for every state action pair. If we just put them all of them in this matrix, then let's call it the fixed matrix. Let's say Q star, capital Q star. So in the limit, okay, some limit stuff going on here, but in the limit, this Q matrix goes, is equal to this Q star. Okay. This was 30 years ago by these 2 researchers. So there's actually a lot of technical nuance that I'm hiding here. So this, first of all, the left-hand side quantity is not exactly a random variable. Okay, so the limit of a random variable going to some fixed quantity, there is some nuance there. But I think at the high level, what it's saying is that the algorithm gets you to the right answer. This is an algorithm which is not the MDP problem, right? It's actually supposed to do trial and error. This is exactly what it's doing here, right? Doing trial and error, but we are saying that eventually it will get you to the right Q values, the best Q values, and therefore once you know the best Q values, you know the best policy. Of course, it's an asymptotic result here. Asymptotic means there's a result which says after long enough time. Okay, this is like in statistics. I don't know if you've seen consistency results, like when little n tends to infinity, you have your estimate is the same as the true parameter. So it's a similar claim like that. Okay. Any questions about this algorithm? Okay, so let's actually spend, now I'm going to just relate it a couple of times to a slightly different algorithm, which is the Q value iteration. Okay, so Q value iteration is for the MDP setting. So let's talk about the notation, right? So Bellman optimality equation gives rise to what is called the Q value iteration algorithm. Okay, so if you ignore the RL setting, right, not the RL setting, in the MDP case, we said if you want to get to Q star, then you just solve a system of nonlinear equations. Okay, and we wrote down the Bellman optimality equation, right? That optimality equation, actually you can make it iterative, and that algorithm there is called Q value iteration algorithm. Q value iteration is the name of the algorithm. Okay, there is a resemblance of this Q value iteration to this Q learning update that we're doing in the previous slide. Okay, in fact, what we kind of, so this is a hand wavy argument. What we're going to do is kind of look at Q value iteration and see that, hey, there's parallels to that in terms of how we are updating the Q function in the Q learning algorithm. Okay, so for that, let me show you the left hand side. So left hand side is this equation here. Okay, this is called I guess this is exactly the Bellman optimality equation, except what changed is instead of equality sign, I just put a right arrow. Okay, I just put a right arrow, and this this is just trying to show an iterative setting. Okay, what is the iterative setting? What you're going to do is start with some random Q values, and then you're going to evaluate the left hand side. Sorry, then you're going to evaluate the right hand side. You start with some Q values, and evaluate the right hand side. You'll get some new Q numbers. Okay, right? Save those Q numbers, and again use those new Q numbers to evaluate the right hand side. Save those Q numbers, and keep doing that again and again and again. Okay, that's it. So it's just, if you have an equation, okay, so you're just evaluating the right hand side starting from some random numbers. That will be the new Q values. Again, evaluate the right hand side. That will be the new Q values, and so on. So it's just, it's an iterative procedure, and that's called value iteration. Okay, whether you can do it for both Q values as well as state value functions, and that actually gets you to the Q star. Okay, in the MDP setting. So okay, so this you start with random numbers, keep evaluating the right hand side, you'll get to Q star. Okay, that's a non-trivial result. First of all, why would that be the case, and why does that work? That algorithm work is beyond the scope of our discussion for today, at least, but it does work. Okay, and so Q learning is also very similar to that. With I've just short formed the notation a little bit here. Hopefully, it's not confusing. It's just saying Q of S comma A is updated with a updating term like this. Okay, so where the definition is like this, right arrow with an alpha just means, hey, take the new X value is the old X value plus alpha times the term that we're adding minus X, or you can say the new X value is 1 minus alpha times the old X value plus alpha times the new value. Remember the moving average idea? So 1 minus alpha times the old value plus alpha times the new value. Or if you just do it in a slightly different way, this is called temporal difference error. So that's what it's saying. So the new value is going to be whatever the old value is plus alpha times this minus the old value. Okay, so you can already see some parallels, right? This term here, R plus gamma max of Q of S prime A prime, looks very similar to this here, right? So I'm justifying, again, this is all hand wavy here. I'm just justifying that if Bellman optimality equation gives rise to something like this, iterative algorithm for the MDP setting, and you can see that our Q learning update is almost, it's somewhat similar to that update in terms of the new term that we introduced, which kind of defines the temporal difference error. It's very similar to that. Okay. So actually, let me spend a couple of more minutes on this. So Q value iteration, like what is Q value iteration doing? If you remember the Bellman optimality equation, it's just saying that Q star of S comma A is related to other Q stars. Okay, Q star of S prime, A prime, and other things. These 4 things. This arc here just means that we are taking a max. Okay, so this arc here just represents that this is not a Bellman expectation equation. I mean, there will be the same diagram here, except the arc just means this arc just means we are talking about stars, and they are related to each other with a max operation here. Okay, so Bellman, so this Q value iteration, all it's doing is focusing on this equality and just saying, hey, I know I need to solve the system of nonlinear equations. Instead of doing that, let me start with some arbitrary numbers here for Q stars, and then keep computing the right hand side. Okay, so with some start in some arbitrary Q stars, keep compute the right hand side, I'll get a new Q star at every state action pair, right? So if I do that again and again and again, that's called Q value iteration. Okay, is that clear what Q value iteration is, or any questions? Okay, so Q value iteration, so the bottom equation here, okay, is exactly the same equation that we wrote here. Okay, So ignore the top equation. It's kind of not super important here. So Q, so all we changed is the equality to a directional arrow like this at the bottom. And what we are really doing is at a state, right? So this actually, the equation at the top is the value function equation for a given policy. So what we're saying is that the state at ST, you'll take an action, you'll get to some state action pair, and from that state action pair you'll get to another state, right? Next state basically. So what's happening with the Q value iteration or the offline case, MDP case, is that all the potential future states that I can get to, all those Q values together, like this one, this one, this one, this one, these are the 4 potential future states, and maybe the Q values, if you want to consider Q values, together influence the new update. The influence and get me to a new updated value of Q. Okay, so old values, there are multiple old values that together get me to a newer value of Q. Okay, so there's some averaging going on, right? Is this clear? So this is just a diagram which shows, hey, in this state you can get to some state action pair. From this state action pair you can get to some next state. Next state you can get to some other state action pair. Maybe it terminates, maybe not terminate. So T is just termination. Okay, it's just a branching of all the potential futures that can happen from this point onwards. So, so what we are trying to show in this diagram is that Q value iteration is going to average across all the future, not average, but like it will consider all the future Q values to take, for example, the maximum of them and take an expectation. Okay, and I just want to contrast that with what we are doing with Q learning. So Q learning is the RL algorithm that we just saw, where what we're going to do is actually just focus on one of these trajectories, because literally we only have an API where we only talk to the environment once, right? So that means we are at some state, we can only take one of these actions, get to one of these state action pairs, get some immediate reward, and from there the environment is going to tell me what the next state is going to be. So it's a bit different from the offline case. In the offline or the MDP case, since somebody told me the full MDP, I can actually take all the numbers into consideration while doing an update. Whereas I just need to take only the numbers that I'm made aware of, which is the immediate reward and next state, to make my update. Okay, so that's one big change. So to summarize, basically the Q learning algorithm, we don't know the model, which means that we don't know the environment, which means we don't know the MDP. We do basically a sampling and an incremental iterative update. Okay, so and we choose the next action to ensure exploration. So exploration part is already clear because we saw that we're doing X1 greedy. And we are gonna, if you think back to the Bellman optimality equation, which is the thing at the bottom, we're going to replace this equality, which is what Q value iteration did, right? But we're also going to drop this summation, because we don't have the summation. We can only talk to environment once. They will tell me what next state is and reward is. So we have to drop this. And so that's exactly what we're doing with Q learning. Okay. Yeah. So if you do sampling, then from a state action pair, you get an immediate reward. Environment tells you what the next state is, but what next action you take is going to be something that you decide later, right? So what is the next action, right? So next action is something that you decide. Yeah, you decide later. So okay, I don't think this is actually very useful. So let me come back to this. So what we're trying to do is drop this summation, and let me directly get to that. The summation. If you drop the summation, you can see that there's a max of A prime there. I'm just trying to introduce that there's a max of A prime there. So let's just focus on that. So what we're basically doing is, yeah, in the state S, we take an action. That then we get back from the environment a reward R and a next state S prime, and that at the next state S prime, we just take a max over A prime from our table that we're maintaining. Okay, so in our table there is some other S prime row where there are different actions. Whatever the numbers are, take the number with the number which is the maximum. Basically, that's what we're doing. Okay. So So this is your Q learning update. All explanation I've given so far is just informal, and it's not exactly does I'm not bucketed into exactly the prediction and control ideas that I showed earlier, but gives you an intuition of how Bellman optimality equation influenced the development of an algorithm, which is Q-value iteration for the offline case, but has also influenced the development of the online version. Okay. So any questions here? So I hope So we saw the last part. What we saw is the Q learning algorithm, and the exploration is there, and the Q learning update. We were just in the past few minutes, we were just trying to justify why that makes sense, and we connected it back to Bellman optimality equation. That's all. We connected it back kind of in an informal way. Okay. Any questions here? If not, then let me summarize this part. And now what I'm going to do is switch over to function approximation, which is a beginning part of next lecture, but I think we can get started there. So let me conclude what we've seen so far in the last lecture and this lecture. It's a framework to make agents. Agents, I just mean software or procedures or computational things intelligent, because they can, as long as you can give this reward signal. Okay, reward signal is weaker than supervisory signal, because reward signal only says how good or bad you are with the action that you took, and doesn't tell you what is the best action you can take at every situation. Is a great way to let as long as you can not spend too much effort in giving these reward signal, an agent can do a lot of trial and error in an efficient way and figure out what's the best thing to do in every situation. Okay, especially makes sense especially if you have a simulator. So if you have a simulator for the stock market, or if you have a simulator for driving in an environment like a car simulator or something like that, then there's no cause for failing. So as long as you can, as long as the simulator, the code can show, hey, you are off the street, or if you're on the street, or you've made a certain portfolio play and then you lost money. As long as the simulator can tell you all that, the agent can learn from all these experiences what's the best thing to do in each situation, right? There are a lot of challenges that's still there. I mean, I only discussed the infinite horizon version to kind of keep things simple. There are all sorts of variations that bring they have their own quirks. There are many algorithms that have been proposed. Q learning is one of them. There are many others, and there are many other considerations also. Actually, what I'll do is not discuss the function approximation. I'll bring it next lecture, but I'll briefly mention the assignment actually now, maybe for the next 5-10 minutes. But where we're going next is trying to tie things back together. So we have the Q learning algorithm, at least the mechanical procedure, if not the intuition. But intuition is just based on Bellman optimality equation. So here's the Q learning algorithm. What we're going to do is, hey, that's not enough, because we have to maintain a matrix, which is the state action value table. Instead of table, can we now, instead of maintaining a table of two functions of two inputs, can I just make it a neural network, for example? Okay, that's what we want to motivate towards. But even if you make it a neural network, it's not enough. So there's some extra, at least empirical ideas that need to be brought in, and those ideas together form an example algorithm called DQN, Deep Q Network. Okay, that's what we'll see next time, and we'll also see how to, maybe one case study with AlphaGo as the example that we were seeing earlier. Okay, so let me. Yeah, so I think I have already discussed this. I wanted to show one last thing. Yeah. So I've been telling, hey, there's an MDP version of the problem and there's a reinforcement learning version of the problem. The MDP version of the problem, where you've already been, your input is MDP tuple, state, action, next state, reward, state, action, transition probability, reward function, and gamma. That's the input, and output is the optimal policy. That problem is also called a planning problem. Okay, it's not a, in contrast to reinforcement learning problem. So planning problem is everything is told you, it's like an optimization problem. Planning, optimization, or offline, all the same things. You know everything about the environment, and then you just compute what is the best policy and things like that. Okay. Whereas reinforcement learning is, you have to interact with the API, and there's a cost. There's a latency. So you have to. There's a learning to get to good policies involved. Okay. So it's a baked in that version. Yeah, and a minor comment about types of parallel agents. The Q learning algorithm is based on value function, state action value function. So that will fall into the first category. But there are many other algorithms, like algorithms which only focus on policies and representing policies and just improving them directly by feedback, which is the reward signal and next state. Those are policy-based algorithms. Okay? And similarly, there are algorithms which both use a policy function or something to do with policy and something to do with value function together to kind of improve themselves and learn. Okay, those are called actor-critical algorithms. Okay, there's a this is just a name, but algorithms can use either the policy or the value function or also a model. Okay, if they use a model, I guess this is the model-based approaches to RL, and if they don't, then it's called a model-free based approach. So Q-learning is a model-free based value function-based approach. Okay, there's also other terms that you may come across, something called on policy, off policy, and so on. So we'll not discuss that. It's beyond the scope of our discussion today. But just wanted to say that we introduced those quantities: policy, value function, and model. You can use any combination of them to define and design your algorithm, okay? Design your solution approach. There are many popular solution approaches. We saw one of them, which is Q-learning, which is based on value function. Okay. Okay, let me just skip these. Yeah. So, any questions here? If not, I'm going to briefly comment about because we only have 20 minutes. I don't want to start a new topic and end in somewhere arbitrarily. So where are we? So again, so we have next lecture on 14th. Assignment due is due on 20th, right? So we have time. And assignment question. So the first two questions are related to bandits, and we've already covered bandits, so you should be comfortable doing that. What we have not covered today yet is for assignment 3, you at least need to know what is a DQN algorithm. I mean, you can always solve the assignment without knowing what's going on, but the DQN algorithm is something that is kind of merges Q-learning with with a neural network. Okay, so that's something that we'll look at in the next lecture. We still have time. What we cover in next lecture. 1 week after that is your submission deadline. So you have 1 week to kind of play around with this. So this question is just, in fact, assignment 4, sorry, is actually intentionally kept simple because you have to work on your project, right? So I don't want to consume too much bandwidth of your project while you are consume too much bandwidth from your projects. So that's why assignment 4 is actually pretty simple and easy to do. So you should get started if you've not yet done first 2 questions. The third question you can wait till next week when we cover DQN to kind of cover it. Otherwise, if you're interested, you can look at the code link here. So this is the link to the repository that we are referring to in the assignment, and you can see that this author and other contributors, they've actually implemented multiple basic RL algorithms, okay? Multiple algorithms. And all of them use PyTorch. So one of the algorithms is the DQN one, which is relevant to our question, but they have other algorithms also implemented. And they also, I think they are, it's already coded with Cartpole 1. I think this is the same environment that you use. Just check that. Yeah, so we are using Cartpole environment. So here are some names, right? So we'll not look at all of them, but here are the names of the algorithm. So it's, reinforce is an algorithm which only focuses on the policy function. So just to give a sense, it's also a simple algorithm. As you can see, number of lines kind of correspond to how complicated the algorithm is. There's a proxy for that. So reinforce is a good starting point if you are interested in an alternate algorithm which is not based on value functions. Okay, so reinforce is a good choice. Actor critic is the one which uses both some sort of estimating policy, estimating policy as well as estimating value function as well. And then DQN is the one which uses value function and does some extra things. We'll talk about it next lecture. And then there are many others, so you can try and look at them as needed. Okay, so yeah, any questions here? Okay, I realize we have 20 minutes of time, but I think I will break early today. Yeah, and if you have questions, you can come to me again, whether it's related to the project or with respect to the assignment or content today. Okay, so we'll end now.